Okay, good afternoon. I'm Markus Eisenbach from Oak Ridge National Laboratory, where I'm a computational scientist working in condensed matter physics and material science. Today I'm going to talk about using HPC for first principles calculations, and then going towards the statistical physics and the simulation of magnetic materials. And the main systems, as I said, we're interested in here are magnetic systems, and they are of a tremendous technological importance for electric machines, i.e. in generators, electric motors, power generation, and to sort of show the advance that has been made in magnetic materials. On the right side of this screen, I show the strength of magnetic materials on this graph as it evolved in the last pretty much 100 years, and the discovery of new materials like these rare earth-based samarium, cobalt, and neodymium-ion boron magnets. And in the insert above, you see a size comparison of magnets that have about the same strength. And it's very important to understand and develop new magnetic materials, as you know, the supply of rare earth materials is very limited. So there's a strong interest in better understanding of magnetism, and then ultimately designing magnetic materials that can compete with these rare earth-based magnets without the use of that large amount of rare materials. So we use high-performance computing to investigate magnetic materials, and we do that at Oak Ridge National Laboratory, which you can see on this slide. And they're basically two very important research facilities we have there to do that. One is on the experimental side, the spallation neutron source, and then the Oak Ridge Leadership Computing Facility, where we host Titan, which currently is the second most powerful computer on the top 500 list. So we use Titan basically to use HPC to get to magnetic material, direct simulations of magnetic materials that are comparable in size to what is accessible from the larger size through experiments. So if you had a 5-nanometer block of iron, for example, you have about 12,000 atoms in this block. That's about around the smallest sizes you can experimentally achieve, but with computation, we're now with large-scale computation, we now come into a range where we can simulate materials of this size directly. So as I'll show you, we get to the range where we can simulate tens of thousands of atoms directly, and we can find both the magnetic ground state of these materials, as well as going towards the finite temperature behavior of these materials, which are very important for technological applications. On this slide, I show you the time scales and length scales we have to deal with. On the very small scale, we can do direct quantum mechanical density functional theory calculations, where we can deal with a few atoms, by now, as I said, up to a few thousand atoms, and at very short time scales. But ultimately, for a real device, we have to go to length scales that approach the micrometer or even millimeter scale, and time scales that are on the order of milliseconds. So we'll have to go. We have to switch between different models, and towards the end of this talk, I will show how we can use HPC calculations to derive more efficient models based on the more accurate first principles quantum mechanical calculations. At first calculation we did a number of years ago, completely quantum mechanical, is a chain of magnetic cobalt ions that are deposited on a platinum surface that has been cut so that there are crystal steps. And experimentally, it has been seen that the magnetic moment on these cobalt atoms arranges in such a way that it has an angle of 43 degrees with respect to the surface. And we have to deal with quite a number of length scales, energy scales, and consequently time scales that are relevant here. The total energy of the system is order of thousands of Rydbergs. Oh, by the way, one Rydberg is the ionization energy of a hydrogen atom, so that is 13.6 electron volts. And then we have the magnetic exchange energy, which is in the order of millirydbergs. And finally, what is responsible for the alignment of these magnetic moments with respect to the surface, the magnetocrystalline anisotropy, quantum mechanical relativistic effect. We can make a model where we embed these steps into a magnetic, into a layer of platinum, and put on these 7 atoms of cobalt, and find the calculated orientation of these magnetic moments completely from first principles using quantum mechanical simulations. And in this movie, you see these 2 different time scales. It started out with the atoms aligned in the plane, and as we start the simulation, they very fast align parallel to each other. That's the energy scale and the time scale of the exchange interaction. And then they very slowly find the ground state direction. And this is the 1,000 times slower process that's associated with the relativistic effects. We find this full convergence, and within about 800 time steps. With the angle we find is in really very good agreement with the experiment. And this is a calculation that is sort of by now on the smaller side of what can be done, but still it contains order of a few hundred atoms. So it's something that would at least require a good-sized departmental cluster to converge. What becomes even more difficult now is if we don't want to understand only one state, but how magnetism behaves at a finer temperature, room temperature, elevated temperature, calculating the Curie temperature at which magnetism vanishes. The calculation I showed you previously was the experiments were done at a very low temperature, cooled with liquid nitrogen or helium. So thermal fluctuations are not very important, but in practical technological applications, you want to understand how you go from a ferromagnetic orientation of the alignment of the material to the non-magnetic you see above the Curie temperature. And finding the Curie temperature is very important in designing new magnetic materials. So the standard theory for quantum mechanical first principles material science is density functional theory. And this is a theory that even its most fundamental approximation, the local spin density approximation, gives a good agreement of the ground state with the experimental value for both iron and nickel. So we find the ferromagnetic ground state, but how do we go to the non-magnetic state? So the exchange interaction that actually form the moments would suggest transition temperature that is orders of magnitude too large. So what actually happens is the moments don't vanish, but they disorder. And this then gives a transition temperature that, at least for iron, is in very good agreement with theory. But to do this, you actually, and for nickel, we are not that good. But to do this, you actually now have to sample over many, many different configurations. So you have to basically pick all possible directions every moment on any atomic site can point at, and sum them up. We can calculate those, and our code is very efficiently parallelized to deal with a large system of atoms. In essence, we can have one atom per compute node or compute threads, and the multiple scattering theory that we use to solve this then boils down to inverting a matrix that describes how each individual atoms interacts with the others, and then requires very minimal communication, basically just sort of the single scattering properties, which are small 30 by 30 size complex matrices between these compute nodes. And the main computation really happens inside this matrix inversion that you see at the bottom inside this circle that sort of sketches out the operations we do. So we need to calculate the density in the first step, then from that's the row there, then from the densities we can calculate the potentials. The potentials give us the scattering, and then the big calculation is inverting about a 4000 by 4000 matrix. And this is really dominated by level 3 BLAS operations. So we get a very good sustained performance for the code that is comparable to the LINPACK number that gets reported in the top 500 list, for example. So we can very efficiently solve the first principles problem, the density functional theory, for a constrained single state of the system. But as I already mentioned, we need to sample over all possible states to get the statistical physics, the finite temperature behavior of the system. And the way to do this is all the thermodynamics is encapsulated in this partition function z there, which depends on the temperature, which I, on this slide, denote by beta, which is the inverse of the temperature. And to calculate this partition function, you have to sum over all possible states of the system, or rather, in our case, since it's a continuous system, it's an integral. And if you have every of these atoms point somewhere on a sphere, this sum there becomes a 2n dimensional integral. So it's impossible, even with the largest computers, to calculate this directly. So instead of that, we use Monte Carlo importance sampling algorithm to get together with the realization that we actually can rewrite this very high dimensional integral in terms of just a one-dimensional integral, where we know the density of the states at a given energy, which is denoted by G of E. And then we have an algorithm to calculate this G of E. So now, if we know G of E, we can calculate the partition function actually on a laptop. But calculating this density of states is what requires supercomputing. And to calculate this, we start out with and that's an algorithm on the right-hand side. Quite a lot of you might be familiar with the standard metropolis importance sampling method that is outlined on the left. We start out by some estimate of G of E, and for lack of better knowledge, we just set it to be constant. We propose moves, that is, we randomly pick a new configuration and calculate its energy and accept the move based on the ratio of the densities of states on the initial and the proposed position. And depending on this, we either accept or reject the move, and then we update the density of states by multiplying it with an update factor at the new energy point the system ends up with. And then we iterate this until we've visited all the energy, all energy with equal frequencies, so that is until we have a flat histogram. And we reduce then this update factor, and it can be shown that as this update factor F approaches unity, this procedure converges to the actual density of states of the system. I'm going to skip this. And it turns out that this is a very efficient way of sampling the system for all temperatures. To illustrate this, I have here a plot that shows the specific heat calculated with this method for now a protein, very simple lattice protein model. both done with a Metropolis method and also with a Wang-Landau method that I just described. And both these calculations used the same amount of computer time. But you see that the Wang-Landau method has a much better convergence in describing the low temperature behavior. If you were to run long enough, ultimately the Metropolis also would capture the structure at the low temperatures, but that would take significantly longer. But even though, so we have this very improved, efficient algorithm with Wang-Landau, and we can parallelize it by having now multiple walkers, but now these different walkers actually need to exchange information, and we can do this by putting multiple instances of this multiple scattering LSMS method for solving the first principles energy of the system for this constrained states onto parts of the machine, and then having one driver node that controls all these walkers, and that allows us to basically use a system of the size of Titan completely for very efficiently calculating this density of states. This is an old scaling plot that was done on the predecessor of Titan, on Jaguar, and you see that this method really scales near perfectly to the full system of that we had available at that time, and the same scaling behavior still holds essentially for Titan. So, as I said, we now can start putting this in and converge the density of states for, in this example, an ion system. And we calculate 250 ion atoms, and we have 400 of these Monte Carlo walkers. And finally, we find this converged density of states in about 5 million CPU core hours, which turns out to be just 2 days on a machine of Jaguars or Titan size. But if you wanted to do that on your laptop or a desktop machine, this would be many years and certainly not practical to do so. So we really need HPC to be able to calculate these seemingly very simple looking calculations that then allow us to identify the Curie temperature of ion, like here by finding the peak in the specific heat. And this calculation found the Curie temperature to be 980 Kelvin, which is a very good agreement with the experiment. And this calculation didn't have any additional input except that we had to know that it is ion. And so another example where we had quite good success is cementite, which is iron 3 carbon, and that's a very important constituent of carbon-rich steels and cast iron. And this has a much more complicated crystal structure, and again converges in a similar time, and we find there the Curie temperature again in very good agreement with experiments at 425 Kelvin for our calculations and experimental values 480 kelvins. So essentially with these HPC systems, it's now really possible to compute free energies of these small nanoscale systems completely from first principles. It still is a very expensive calculation requiring many millions of CPU hours. So it's something that is not and probably will not for a very long time be possible to do on smaller clusters. So HPC systems really are important in this case, but it really gives us a completely parameter-free way of finding answers to the calculations of the Curie temperature that are basically within a few percent of the experimental value and pretty much have error that is similar to the error that underlies the approximation to the many-body quantum physics that is that we employed in the form of this local density approximation. So to change gear a bit, I showed you that we have been able to really calculate the Curie temperature for these systems completely from first principles. But it still is a very expensive calculation. And also it leaves out other important aspects like the movement of the atoms. And doing this completely from first principles is still not feasible with current generations of supercomputers. We'll probably wait for the successors of the current systems and beyond to be able to do this completely from first principles. So now to incorporate the movement of atoms, in this case the lattice vibrations, into understanding the magnetism, we are going to derive effective models that allow more efficient calculation of small clusters from large first principles calculations. So it's really using HPC in an efficient way to get a model that then can be studied into more detail with less expensive computational resources. And to do this, we generate, we want to understand how do the magnetic interactions in the system change as the atoms move around. To do this, we generate using standard molecular dynamics configurations of ion atoms that correspond to a temperature just below the Curie temperature, 900 Kelvin in our case, and take snapshots of those. So in the picture here you see as black the ground state positions of the ion atoms, and in red snapshots where they are at a single instance at this high temperature. So we take this and we use the large LSMS calculations to calculate the energies for different magnetic configurations that we impose on those to be able to fit the magnetic exchange between these sides. So each pair now has a different exchange interaction. So to get all the pair exchanges in this even small sample of 128 atoms that you see here, we still need many tens of thousands energy calculations. So again, this is something that requires many tens of thousands, hundreds of thousands of hours of CPU time on HPC computers, and something that is not easily done otherwise. But once we have this, and all these pair exchanges of Jij that come out of these calculations are represented by these black circles, and you see it's quite complicated behavior that not only depends on the separation between the pairs, but also what the environment is and where all the other atoms are. So a simple fit that just takes the separation into account, which would be the green line here, doesn't really do justice of the functional form of this interaction. So we have been able to derive a more complicated functional form fit to this data in terms of the separation and the local atomic volumes and the distortion of the volumes. So in a sense, not only where the two interacting atoms are, but how their environment looks like from these calculations. So we can come up with a fit that represents these interactions quite effectively in form, and you see that in the form of these red squares. And taking all these information into account, we can calculate the specific heat of iron now from this model using Monte Carlo. And this graph you see here in black, the experimental values for this total specific heat of iron. So that's both the atomic and the magnetic contributions to the specific heat. And the triangles show our calculation with this model that allows for the interaction for the interaction between the atomic degrees of freedom and the magnetic degrees of freedom in the system. And for comparison, in the red circles there, we exclude this interaction. So you see in the shaded area between these two curves the importance of the contribution of this interaction between the magnetic and atomic degrees of freedom for the specific heat, especially near the Curie temperature. And to be able to identify this, we really needed this interaction between first principles, large-scale first principles calculation to discover this interaction, as well as advanced Monte Carlo calculations on this model to do this evaluation at this level. Magnetization. So another important contribution to magnetism and understanding magnetic materials is that crystals are not perfect. So you have defects, dislocations, and they are very important for understanding the structural behavior of materials. So what are the mechanical properties ultimately of things like steels or nickel alloys? And it turns out that since all of these important structural materials also are magnetic, and understanding the magnetism at these dislocations is of great importance. So here we have done a large-scale first principles calculation. Again, something that is only really possible if you have at least hundreds of compute nodes available for a system of that contains 4 screw dislocations, and you see that close at this dislocation force, where the screw dislocations are located, the magnetic moment that is shown in the left picture is significantly enhanced over the bulk equilibrium moment. And on the right, you see that the introduction of this dislocations really distorts the lattice and changes in the local volumes of these iron atoms. So then combining this with the first principles derived model for the magnetic interaction and the movement of the atoms, we now can see how this magnetic moment changes as we increase the temperature. So now we're at temperature just about 100 Kelvin, 80 Kelvin below the Curie temperature of the system. And there you see now that where the magnetic moment originally was enhanced near the dislocation cause, it is now considerably suppressed compared to the bulk value. So the dislocation cores are located at these blue spots. So now we're really able to see how the interactions, magnetic interactions in these systems change based on the change in the atomic environment. And in the final piece of talk, I going to go from the thermodynamics to the actual dynamics of magnetism in combination with atomic motion. So to do this, we introduce in our model the anisotropic exchange that again has to be derived from relativistic first principles calculation. So this is really the interaction you saw in the movie right at the beginning that was responsible for aligning the magnetic moments with the underlying surface. Now this is actually, as we move the atoms around, represents some torque and preferred direction that drags in the direction of the magnetic moments with it, and that ultimately will allow the transfer of thermal energy and of angular momentum between the lattice and the magnetic system. So this is the actual physical mechanism that ultimately transfers heat to the spins. And we can estimate this magnitude of the transfer from, again, this large scale first principles calculation, and you need again many tens of thousands per calculation to get these quantities. And now with this more complete model, we now can combine the molecular dynamics and the spin dynamics simulation and see in this plot here how the magnet equilibrates, the dynamics on how the magnet equilibrates with the underlying lattice. So in these plots you see the temperature of the atoms of the lattice that's coupled to a thermostat, and that's in the top two plots the blue line. And then we start out the spins all aligned in a single direction and let them thermalize with the lattice. And you clearly see how the speed of this depends on the temperature as well as and the final total magnetic moment per side that is achieved in these two different temperatures. So to conclude this final part of the talk, we have shown that even though the distribution of the local magnetic moments is not uniform, but it's affected by this local atomic environment. And in BCCI, that atomic effect, the effect of the atomic distance and the local volume basically cancel each other. And we see that already for finding the Curie temperature itself, the uncoupled systems works well, but the coupling itself is important to understand the complete specific heat, and we also have seen how we can apply that to complicated dislocation system and ultimately to the dynamics of magnetism. And this work has been done by myself and my colleague Yinghua Li at Oak Ridge National Lab, Don Nicholson, who's now at the University of North Carolina, Nashville, and Odd and Jinchi Yin, who are at the University of Tennessee, Greg Brown from Florida State University, and David Landau and his student Delina Pereira from the University of Georgia at Athens. And this research has been funded by the DOE Office of Science, Basic Energy Sciences, as well as advanced scientific computing research. Thank you for your attention.
I have a question. To compare the Wang-Landau algorithm versus the Metropolis algorithm, which one is easier to parallelize, and can you use accelerators? Or how easy is to use accelerators?
For these calculations, we actually don't use accelerators because the main work is really in the solution of the first principles. So it still is. So there's no need for us. There was no need to put the Monte Carlo itself on accelerators. And as soon as you have to deal with random numbers on accelerators, things get complicated. But it's doable, and it has been done. Both of these algorithms have been put onto accelerators in the past. What is certainly Metropolis is easier to parallelize because there each Walker is essentially can be essentially independent. So you can have a large number of completely independent Walkers running completely independent of each other, and you just average the result at the end. And basically using the central limit theorem. Since the acceptance probability in Wang-Landau depends on the simulation itself, you need some communication between the walkers. And so Wang-Landau is much harder to parallelize. I mean, much harder compared to something that is trivial to parallelize. The way we've done it here, it still is very simple. You only, since we have this master-slave and the parallelization in our scheme, there's actually no parallelization at all at the Monte Carlo level itself. But you still have multiple walkers that go along, and you just spawn the energy calculation, collect the states as they come back. There are some problems with this to go to very large numbers of walkers that have to do with basically walkers getting stuck in very low probability regions until most walkers come there. So there are advances of this method that really specifically address parallelization, like replica exchange Wang-Landau, that has even better convergence than what I've shown here, but it's significantly harder to implement because you really have to exchange large amount of information between the different walkers. In a sense, it's somewhat similar to parallel tempering or other replica exchange methods.
Thank you.